Howdy everyone, welcome to Computer Graphics Rendering. In this video we're going to talk about closest fit shaders and bidirectional reflectance distribution functions, or BRDFs. Let's get started. Let's go over the topics. First we're going to go over the ray tracing pipeline and review that and see where closest fit shaders fall in the timeline. Next we're going to go over closest fit shaders, talk about what we can do with them. Then we're going to talk about what bidirectional reflectance distribution functions are, talk about the frame of reference, so what are the angles that we're thinking about, and lastly talk about what are some of the rules that physically based BRDFs have to have. So the ray tracing pipeline, we want to start out with ray generation, and in this case we might be sending rays from a camera or from a surface or some other criteria for that. So we go ahead and start by beginning by tracing the ray, and to do this efficiently we use a ray traversal acceleration structure. This could just be a simple loop over the objects, check for intersections, or it could involve more complex things like octrees or voxels. And so what we want to do is run it through an intersection shader. So we might have something for triangles, something for spheres, and so on. And if we get a hit, then we can go ahead and run any hit shader, and this is useful for a lot of things that we talked about in a previous video. If we have run out of objects to check against, then we might have a hit. And so if we didn't have a hit, then we call a miss shader, and we might use this for a physically based sky model. But if we do have a fit, then we'll call a closest hit shader. So let's take a look at those. So in this closest hit shader, we've been talking about weighted style ray tracing recently, so one of the particular rays we were interested in are reflection rays. And reflection can be calculated as the difference between the original light vector and by projecting the light vector onto the normal. And that basically just mirrors the original vector about the normal. Secondly, we would like to do refraction. And refraction, we're trying to find an angle that's going into the surface, and to do this we need to know the index of refraction. So what we'll do is we can calculate this using this equation over here, which is essentially we use the ratio of the index of refraction, and we use the cosine of the angle between the normal and the light vector. And if you remember Snell's law, there's a sine involved in there, so what we do is, because we can't calculate the sine, we just simply take 1 minus cosine squared, which is a trig identity, and essentially we can use this to calculate how that angle is, how the light vector is bent towards the normal. And then nextly, shadow rays, which is our method of finding out, well, what's the contribution from each light source. So if an object is going to be in shadow, it's going to be blocked by another object, and then if it is able to make it to the light, then we can go ahead and calculate that contribution. And we do this by way of what's called the rendering equation. And the rendering equation basically relates the amount of incoming light to outgoing light. And this is the more general case that you might use for path tracing, but essentially what we are interested in is finding out, if we have a point X on our surface, how much light is leaving that surface in the direction omega O, and we use that to represent the view direction. So we say that it's a combination of, one, any emitted light. So if this object produces light, then we call that L sub E for emitted light. And then what we do is we treat every angle coming into the point X as a potential source of light. And so we integrate over a hemisphere, or if we're dealing with refraction as well, the entire sphere around the point X. And we use a function called f sub r, which is the BRDF, to relate how much incoming light is reflected from the incoming direction omega I. And so we will go ahead and look up and find out, well, what is that light? And so this is kind of a recursive definition. And then we use the dot product of omega I and omega G. And if we use the left angle and right angle brackets around that, we basically are saying we want to take the positive product. We clamp it from 0 to 1. A dot product can go from -1 to +1, so we want to clamp that. Okay, so let's go ahead and start talking about, or let's draw this picture out by looking. We'll draw the picture in just a second, but we're going to talk about what BRDFs are available for us to use. So BRDFs, bidirectional reflectance distribution functions, can be thought of in maybe two categories. First are specular, and secondly we have diffuse. And the difference between the two is that specular BRDFs are trying to model reflections, and diffuse models are trying to model scattering. In other words, like your walls would be diffuse, so they reflect light in every direction. So for diffuse models, the most easiest one to implement is just simply to calculate the dot product between the normal and the light, which is Lambert's cosine law. This one is basically just saying that when light hits, it's evenly scattered in every direction. However, this can be a bit simplistic because the microgeometry normally doesn't scatter light that evenly. So for example, dusty surfaces like the moon don't reflect light in this kind of way. So one model is called the Oraneer, which kind of models light from a dusty perspective or all the way down to Lambert's. So it's very flexible. I like to think of it as a dusty diffuse model. And then recently, in the last few years, there's one by Disney that also takes into account the Fresnel effect, which I think kind of gives the ability to model fuzzy surfaces like felt or velvet. So there's this particular one. Now, when we're talking about specular, we're talking about reflection. So shiny surfaces. So one of the most famous models is the Phong model, which models a highlight based off the reflection vector, and then but it's not physically based. So a newer one is called Blin-Phong, and this one is physically based, and this one uses the half angle vector, which we'll talk about in a little bit, rather than the reflection vector to base the highlight on. And then we have the Cook-Torrance model, which uses a Beckmann distribution, so it tries to model a Gaussian surface, and the Cook-Torrance one is used for a lot of different surfaces, and it also kind of has a form that all these other ones typically use. And then lastly, GGX is another fairly recent one. This tries to model surfaces as if they had spherical particles inside of them. So sometimes it's good for modeling metal, whereas at Cook-Torrance, I think uses a V cavity model, which is a slightly different way of modeling microfacets. And microfacets are, if you can think of the geometry as a flat surface, right? We're using polygons to render. Then microfacets represent a rough version of that. So by way of illustration, let's imagine that this bright blue line is the geometry. Then the microsurface or microfacets might look something like this, or a V cavity type model where we just use these grooves to simulate what happens if there's like shadowing or masking, or something like this where we kind of imagine particles suspended and they're reflecting almost like they were ellipsoids or some kind of other material. So this is something that we're going to differentiate. So let's go ahead and look at what the frame of reference is. So let's find out what all the directions that we might be interested in. So when we say frame of reference, we're essentially wanting to draw a diagram where we can understand all the directions involved in the equation, the rendering equation. And so here's a slightly shorter version where we just basically say that the outgoing light is equal to any emitted light plus the integral of all the incoming directions multiplied with the BRDF, F sub r, and the dot product between the incoming light vector and the geometric normal. So just For way of reference, sometimes you'll see these equations use different variable names. So we might see n, and this is the same thing as omega g, and we might have the vector L for the incoming light, and so we'll say this is omega I. We have the outgoing view vector, and we'll say this is omega O. We would have the reflection vector. We'll say that's omega R. The transmitted light vector, so the refraction, so we'll call that omega T. And then we might have, this is not normally modeled, but we might say omega M represents the angle of a microfacet. Then we have the reflection vector. Oh, sorry, we just mentioned the reflection vector. The half angle vector, which is omega H, which is the same thing as the light plus the view over 2. And what this gives us essentially is, well, what is the direction that the microfacets would be mirrored around? And this is what we're going to use this for. Okay, so let's draw this picture. So we have the surface. So this is our geometric surface. And so we have a geometric normal, which is orthogonal to our surface. Excuse me. And so we will call this omega g. And essentially what we want to do is treat every direction as a light source. And this hemisphere is what we're going to call omega. Now, we could also say that we want to model scattering just in a general way. We might call this the BSDF, or bidirectional scattering distribution function, where we're trying to consider not just reflected light, but also internally scattered light, such as marble or skin, different things like that. So we would use the BSDF, or sometimes we'll split the BSDF, call it the bidirectional transmittance distribution function and the bidirectional reflectance distribution function. So we have the outgoing vector, the one we're interested in, which is omega O, and we have an incoming vector, which is the incoming light direction, or omega I. Now, if we add those two vectors together, then we'll get something that's pointing halfway, and we'll call that omega H. And then we might want to find out what the reflection vector is from the incoming light direction, and that would be omega R. And if we have incoming light, then, and we want to find out how it will refract, then we will have omega T representing that refraction angle. So these are essentially all the angles that we're interested in when we're trying to model the BRDF, which I mentioned is F sub R. And this takes two angles, omega I and omega O. And it just relates how much light is reflected. And one way to think about this is to think about the incoming light and the outgoing light. If you want to take the ratio of incoming light to outgoing light, then we would basically say that that ratio is the BRDF. It's a function that essentially relates how much light is reflected in a certain direction. So lastly, let's go ahead and take a look at what are some essential rules that are physically based BRDFs, what they have to follow. So let's look at some rules for physically based BRDFs. 1, we have conservation of energy. This means that we can never reflect more light than comes in. Mathematically, this means that if we were to integrate the entire hemisphere over our BRDF f sub r, that in total it should be less than or equal to 1. Secondly, it needs to obey Helmholtz reciprocity. In other words, the order of the angles omega I and omega O, they can be swapped. So the function has to essentially say that if you shoot a ray from the other direction, in the exact same direction, then you will get the exact same ratio. And then with third, we have positivity. This means that our BRDF has to be greater than 0. In other words, there's no way that we can reflect negatively. In other words, it doesn't act like a vacuum for light. The only way that this works in practice, essentially, though, is that if you're adding transmittance, in other words, translucent objects, then this might act like this, but you have to make sure that you then sum the entire sphere. And then lastly, we want to talk about, when we're talking about microfacet models, conservation of projected area. So normally the cosine between the light and the normal reflects this this value, and of course the cosine kind of limits, we're dealing with a flat surface, but when we're talking about microfacet models, we're adding additional area to the surface. So the way that we do this is by relating the masking function, which we call G1, omega O, which talks about how much of the reflection based on the microfacets is in shadow, that the cosine between the geometric normal and the outgoing direction cannot be greater than the cosine. So here's a little diagram. So we have our flat surface represented by the bright blue cyan line, and the microfacet model, which is represented by the pink curve. And so what we're essentially saying is that we can't have more area when we project this out in direction than the cosine. So some models will obey this, some will not. And then lastly, I just wanted to go over the equation for a specular reflectance model. I'm just going to erase this top part real quick. So we have what's normally known as the Cook-Torrance model, which basically says that the reflectance of a microfacet model is dependent on one, the microfacet distribution. So this basically says how many facets are pointing in this direction, how many microfacets are pointing in a different direction. So this is represents that function. And then we have the Fresnel reflectance, and this is based off the angle between the half angle and the outgoing direction, the incoming direction of light. And then we have the masking shadowing function. And you'll see this is G2 instead of G1, and what this means is that we're taking into account both the masking shadowing from the incoming direction and the masking shadowing from the outgoing direction. And then on the bottom, then we are saying that it's in proportion to the cosine between the normal and the incoming direction of light, and the normal and the outgoing direction of light. And so just as one quick example, the Blindfung microfacet model can be thought of as, so we have the geometric normal and the half angle. And this is, we might have a certain amount of roughness associated with this. So we use alpha squared to represent the roughness of the surface. And then we take the dot product of the normal and the half angle, and we raise that to a power 2 over alpha squared plus epsilon in order to avoid some numerical issues. And minus 2 plus epsilon. And what this will simulate is a shiny surface. So this is basically just saying that we take the dot product between a half angle vector and the geometric normal, and we raise it to a power, but we have to also make sure that it obeys these conservation laws, and so this is called the normalized Blin-Phong microfacet model. And so this was just a quick example of what physically based BRDFs, how they look, and some of their features. So just to go over the just review, we talked about the ray tracing pipeline and how we get the closest hit shaders. That's kind of at the end, and the things we might want to do with them. So we talked about different bidirectional reflectance distribution functions, specular models, and diffuse models. Then we kind of talked about the frame of reference, so we get an idea of what all the different vectors that we need to use, where they are, how they point. And then lastly talked about some of the characteristics of physically based BRDFs, such as the need for them to be to obey conservation of energy, positivity, Helmholtz reciprocity, and conservation of projected area for microfacet based models. So thank you for watching this video. Hope you have a good day. Like to just tell you adios.